Section 3.5 gives us some very specific real-world modeling scenarios that we have, particularly in science, that we can use for logarithmic and exponential equations. The essential question here is, what are some of the ways we can use exponential equations to model real-world situations? And some of the key terms we're going to have here is exponential growth and decay, specifically with half-life, and then something called Newton's law of cooling. You are most likely already familiar with this, but first let's go ahead and define exponential growth and decay. So typically our formulas will all have the same format, where it's either going to be a function or it's going to be some amount value. It's going to be equal to the initial amount times e to the kt, or e to the negative kt. So if the kt is positive, you're going to have exponential growth like we have in this first graph. If the k is negative, we're going to have exponential decay, like in our second graph. Our first example is modeling the growth of the population in the United States. So on the right here you see a bar graph of the populations in specific years, and we want to find an exponential growth model that models this data. So we want to come up with an equation for 1970 through 2007, and then we want to figure out which year the population is going to reach 315 million people. So here we start with, alright, so here we're going to find the model first for this type of data. So we always start with our basic equation. So the amount is going to be equal to our initial amount, e to the kt. And what they've given us here is, let's go ahead and use this first year and this last year on our bar graph. So if we let the last year represent our a value, so a is going to be equal to 300.9, which represents the millions of people. Our initial amount in 1970 is 203.3 million. And then we're going to find e to the k, and the elapsed time between both our values is going to be 37 years. So what we need to do first for part A is we need to solve for k to find our growth rate. So by taking what we've learned in the previous section, we're going to solve for k here. So the first thing I need to do is divide both sides by 203.3. So that gives me 309 divided by 203.3 is equal to e to the 37k. And now if I take the natural log of both sides, I get 37k ln e, and remember that's just 1. So k is equal to the ln of 300.9 over 203.3. All of that is divided by 37, which is equal to 0.010597. Of course, I used a calculator to figure that out. So our model here is going to be A is equal to, our initial value is 203.3, e to the 0.0157, and then t. So that's our model. So the second part wants us to figure out in what year the population will reach 315 million. Alright, so let's start with our model. So here, A is going to be equal to 203.3, and remember that's our initial value, e to the 0.010597t. And we want to figure out how long it's going to take, or the time value, for the population to reach 315 million. So if A is 315, we basically plug that into our equation and solve for T. So the first thing I do is I divide by the 203.3. Is equal to the e to the okay, and then we're going to take the natural log of both sides again. And hopefully by now you're starting to see the pattern is really the same for just about all of these problems. And remember, the ln of e is just 1, so that kind of goes away. So T is going to be equal to the ln of 315 divided by 203.3 divided by our k value. And when we plug that into the calculator, we get 41.3214, or approximately 41 years. Okay, so keep in mind that that's 41 years after our initial time, which is 2070. So 41 years later, it's going to be the year 2011. So please here take a couple seconds, recheck point 1, work it out, and then I'm going to give you a couple seconds to pause the video, and then after you've worked it out, you can unpause it and see the result. Okay, so in part 1 we start with the given population in 1990, which was 643 million, so that's A naught. And in 2006, our final value is 906 million. And the number of years difference between 1990 and 2006 was 16 years, so that takes care of the time. So now here, we start by dividing both sides by 643. Take the ln of both sides here, and then we solve for k to get the ln of 906 divided by 643. All divided by 16, and our k value is right here, 0.021431. And then we plug that into our model here to give us the model of population growth. So part 2 is asking us, in what year will the population reach 2 billion people? So A is just going to become 2000, and then we go through the same process we've done in the previous problems, but this time solving for T. And when we go through that, we end up with 52.94, and here we're just going to assume that's 53 years. Now please remember that's 53 years from our initial date, which was 1990. So 53 years after 1990 is the year 2043. The second type of problem we're looking at is our typical half-life problems. This is used when we're looking at like carbon dating of certain things. That's the most popular way we use half-life. Or looking at the amount of time it takes for something to decay, like radioactive explosions and whatnot. So here we're going to look at part A, which says use the fact that in 5,715 years, a given amount of carbon-14 decays by half, which all that means is, let's say I have 100 grams of carbon-14, in about 5,700 years, I'll have 50 grams. So we want to use that fact to figure out just the general model for carbon-14. So let's start with the equation here. So that's A is equal to A naught E KT. Okay, so what we want to know is, we know that in 5,715 years, the amount that's left will be half of the original. So rather than put any numbers in, what happens here is A becomes A naught divided by 2. And that's going to be equal to A naught e to the k, and then t is 57/15. Okay, and what's really nice about that is both A naughts are going to divide out, which gives me 1/2 is equal to E 5715 K. And now we can simply solve for K like we have our variables in the exponent previously. Ln of 1/2 is equal to 5715 K. So K is equal to the ln of 1/2 divided by 5715. So K is going to be equal to negative 0.000121. Okay, so our model here, A is equal to A naught e to the negative 0.000121 t. Okay, and that we were able to find the amount of time it takes for half of any material. So in part B here, they want to know how, in 1947, a jug found the Dead Sea Scrolls, and they figured out that the wrappings contained 76% of the original carbon. Okay, so they want to know how old are the scrolls. So 76% of the original, when I substitute that in for A, that translates into 0.76, because that's the decimal value for 76%. A naught is equal to A naught e to the negative 0.000121 t. And again, let me reiterate. So this statement says 76% of the original is equal to the original and then e to the kt. So here we're going to solve for time. So in doing that, we end up with 0.76 is equal to e to the negative 0.000121 t. So the ln of 0.76 is equal to negative 0.000121 t. So t is equal to the ln of 0.76 negative 0.000121. And we calculate that out to be 2,268 years old. So that's how old the Dead Sea Scrolls are. For the checkpoint, I'd like you to find the equation for the half-life of strontium-90. The half-life is 28 years, so find that model. And then figure out how long it's going to take for strontium-90 to reduce from 60 grams to 10 grams. Go ahead and pause the video, try to work it out, and then check your solution when you're done. Alright, so again, we start with our A naught divided by 2 because that represents half the initial amount. Remember, that's what we're looking at in half-life problems. So that gives me 1/2 is equal to e to the 28k. And then I'm solving for k, so ln of both sides. And we're able to figure out k is equal to negative 0.024755. So our model is right here. A is equal to A naught e to the negative 0.024755 t. And that's for part A. For part B, we're going to take that model, and A naught is going to be 60 because that's the amount that was released into the atmosphere. And we want to know how long it's going to take to have 10 grams left. So 10 divided by 60 is 1/6. And then again, we use the same process to solve for T. When we do that, we get T is equal to 72.379 years. Our next example we're going to look at here is anytime we're looking at something cooling, it follows what's called Newton's law of cooling. So if I make a cup of coffee and it starts out at 140 degrees and cools down to the room temperature, which in our classroom is sometimes right around 67 degrees, what is the shape of that graph as it cools down? So if I were to kind of sketch it out, so there's our axis. So it starts out here at 140 degrees, instantly starts to cool down, and then it levels off. And right there where it levels off is the temperature of the room. That data can always be modeled to this equation. So the final temperature is equal to our initial temperature, our room temperature for C. T naught is our initial, and then our room temperature, and then e to the kt. So it's not a lot different than we've done in the past. There's just a couple more variables here we have to account for. So here we want to look at a cake is removed from the oven that has a temperature of 210 degrees. It's left to cool in a room that has a temperature of 70 degrees. After the 30 minutes, the temperature of the cake is 140. Part A asks, use Newton's law of cooling to find a model for the temperature of the cake, T, after lowercase t minutes. So let's start with the model. T is equal to C plus the quantity T naught minus C e to the kt. Okay, so they give us the temperature, which is the initial temperature is 210 degrees, the room temperature is 70, and then the final temperature, or T in this case, is 140 degrees. So capital T is 140 is equal to 70 plus 210 minus 70 e k, and then T is 30. So we're going to quickly do some algebra here. So this left-hand side, if I move over the 70, it's going to become 70. 210 minus 70 is 140, and that's e to the 30k. And then we can use the process we've learned in the past, and hopefully you see the pattern by now. To solve for k, it's going to be equal to here, the ln, and first when I divide the 70 by 140 I get 1/2, so it's the ln of 1/2 divided by 30, so that gives me a k value of negative 0.023105. So our model of this is going to be T is equal to 70, because that's our room temperature, plus, and we can just write 140 here, because that's always going to be our initial temperature minus our room temperature, e to the negative 0.023105 T. So that's our model. So now they want to know, what is the temperature of the cake after 40 minutes? Well, that example is quite easy. All we have to do is plug in 40 for T. So again, here we start with T is equal to 70 plus 140 e to the negative 0.023105, and put a 40 in, and that quickly calculates out to 125.6 degrees. Okay, so that's part B. Part C says, when's the temperature of the cake going to be 90? So again, our capital T becomes 90 here, is equal to 70 plus 140 e to the negative 0.023105 T. So when I subtract the 70 over, I get 20. 140 e to the negative 0.023105 T. So 20 divided by 140 is 1/7, and that's going to be an ln. So the ln 1/7 is equal to negative 0.023105 t. So t has to be equal to whatever the ln of 1/7 divided by our k value, which that is equal to 84.2 minutes. So that's the total time it takes for a cake to cool down to 90 degrees. Alright, so for checkpoint 4, you're given an object that's heated to 100 degrees Celsius and let to cool in a room that's the temperature is 30 degrees Celsius. Find the model, then find the temperature after 20 minutes, and then find out when the temperature will be 35 degrees. I'm going to give you a couple seconds and I'm going to pause the video. You please go ahead and pause and then calculate it out and check your work. Okay, so first we're going to take our known values. We start with the model first, which is right here. Then we take our known value. So for our initial problem, the final temperature is 80, our room temperature is 30, and then our initial temperature is 100, and of course minus the 30, and then e to the, it was 5 minutes, k. So we want to solve for k. So again, we went through the process here, and again, it's all the same. It's really, by now you should see the pattern. So k is going to be equal to the ln of 5 divided by 7 divided by 5, and k is equal to negative 0.067294, which gives us this model right here. Okay, so that's the solution for part A. Part B is just asking us what the temperature is after 20 minutes. So we take our model and plug in 20 for T. And when we do that, you see right here, we get T is equal to 48.2 degrees Celsius. So for part C, we're just trying to figure out how long it takes for the object to be cooled to 35 degrees Celsius. And so we start with the model and just plug in 35 for our capital T, and we're solving for lowercase t. And again, the pattern is going to be the ln of 5 over 70 divided by our k value should give us the total time of 39.2 minutes. Okay, so your homework on this section is on page 447. It'll be 1 through 5. Those are all population-based problems. 17, 27, and 31 are half-life problems, and 47 and 48 are Newton's law of cooling problems. Have fun.